This lesson will explain what a chemical equation is, what it represents, the parts of a chemical equation, and finally we'll take a look at how to balance chemical equations. A chemical equation is a written representation of what happens during a chemical reaction. It includes chemical formulas and symbols. Please remember that a chemical formula is the shorthand representation for a compound, and a symbol is the shorthand representation for an element. Let's start by taking a look at this example of a chemical equation. This equation is the representation of the formation of water vapor from hydrogen gas and oxygen gas. The substances on the left-hand side of the arrow are referred to as the reactants. They are the substances that obviously react in the reaction. The substances that are on the right-hand side of the arrow are called the products, and they are produced during the chemical reaction. The arrow that separates the reactants from the products is called the yield sign. It's very similar to an equal sign in a mathematical equation. The numbers that are sometimes written in front of the reactants or the products are called coefficients. As we will see shortly, coefficients are used to balance chemical equations. In this particular reaction, all of the substances are gases. We indicate this by putting the lowercase g in the equation. This g is a physical state symbol. If the substance was a liquid, liquids would be represented with a lowercase l. If the reactants or the products were solids, the physical state symbol would be a lowercase s. And if the reactants or the products were aqueous solutions, we would indicate this by putting an AQ in parentheses. Please understand the difference between aqueous solutions and liquids. Liquids are pure substances, whereas aqueous solutions are solids that are dissolved in water. A chemical equation can be thought of as being a recipe for a reaction. In this particular example, we have 2 molecules of hydrogen reacting with 1 molecule of oxygen to form 2 molecules of water. The coefficients in the balanced chemical equation can also represent the ratio of the number of moles that react. You can also say that 2 moles of hydrogen molecules would react with 1 mole of oxygen molecules to produce 2 moles of water. So the coefficients can represent the number of molecules that react. The coefficients can also represent the number of moles that react. Please note that the coefficients do not directly tell you the proportion of the masses of reactants and products that react. In order to calculate the masses of substances, we'll need to do a little bit of math. Using the molar masses that can be found on the periodic table, 2 moles of H2 hydrogen gas would weigh 4.04 grams. 1 mole of oxygen O2 would weigh 32.00 grams. And if we would calculate the mass of 2 moles of water, we would get 36.04 grams. You may have noticed that the mass of the product formed in this chemical reaction is equal to the sum of the masses of the reactants. This will be true in any chemical reaction. The mass of the products will always be equal to the mass of the reactants. Since this is always true, it is called a law. It is the law of conservation of mass. In addition to the masses being equal, the number of times each atom appears on the reactant side and the product side of a chemical reaction must also be equal. In a chemical reaction, bonds break, atoms rearrange, and new bonds form. However, you are not creating or destroying any atoms. This is called the law of conservation of matter. Let's look at our previous example where hydrogen and oxygen react to form water. On each side we have hydrogen atoms and oxygen atoms bonded in different ways. Let's tally how many are there before the reaction and after the reaction. On the left-hand side, on the reactant side, we have 2H2. That would represent 4 hydrogen atoms. O2 represents 2 oxygen atoms. On the right-hand side, we see 2H2O. That represents 4 hydrogen atoms and 2 oxygen atoms as well. This illustrates the law of conservation of matter. The numbers and kinds of atoms that we had before the chemical reaction are the same as the number and kinds of atoms that we have after the chemical reaction. Again, simply bonds have broken, the atoms have rearranged, and new bonds have formed, but we haven't created any matter, we have not destroyed any matter. All chemical reactions must be balanced to ensure that you are obeying the law of conservation of matter. Let's take a look at the next example. In this reaction, we are reacting zinc with hydrochloric acid to form zinc chloride and hydrogen gas. On the reactant side, we have zinc, hydrogen, and chlorine, and we have those same atoms on the right-hand side. As it's written now, we have 1 zinc atom, 1 hydrogen atom, and 1 chlorine atom on the left-hand side. On the right-hand side, we have 1 zinc atom, 2 chlorine atoms, and 2 hydrogen atoms. This reaction does not yet obey the law of conservation of matter, so we need to balance it. If I place a coefficient of 2 in front of hydrochloric acid on the left-hand side, that will change the number of hydrogens and chlorines on the left to 2 hydrogens and 2 chlorines. The reaction is now balanced and obeys the law of conservation of matter. Let's take a look at yet another example. In this reaction, I'm reacting aluminum oxide with lead to form lead 2 oxide and aluminum. On the reactant side and the product side, I have aluminum atoms, oxygen atoms, and lead atoms. Let's set up our tally. On the left, I have 2 aluminum atoms, 3 oxygen atoms, and 1 lead atom. On the right, I have 1 of each type of atom. Let's start by balancing the aluminum atoms. If I put a coefficient of 2 on the right-hand side in front of aluminum, that will change the number of aluminum atoms on the right to 2. Next, I'll attempt to balance the oxygen atoms. By placing a coefficient of 3 in front of lead oxide on the right-hand side, that will change the number of oxygen atoms on the right to 3. The oxygens are now balanced. However, by placing that coefficient of 3 in front of lead oxide, I've also changed the number of lead atoms on the right-hand side to 3 as well. Now the lead atoms are not balanced. To rectify that situation, I'll place a coefficient of 3 in front of the lead on the left-hand side, thus changing the number of atoms of lead on the left to 3 as well. Now this reaction is completely balanced, and it follows the law of conservation of matter. Now I'm going to show you a little shortcut for balancing reactions that contain a polyatomic ion. Polyatomic ions can be balanced as a group as long as the group remains together as the polyatomic ion on the product side of the reaction. Here's an example that illustrates that. In this particular reaction, I am reacting silver nitrate with barium chloride to form the products silver chloride and barium nitrate. The polyatomic ion nitrate appears on both sides of the reaction. Therefore, I can treat it as a group. Let's create our tally underneath this reaction. On the reactant side, I have silver atoms, I have nitrate ions, I have barium atoms, and I have chlorine atoms. I have the same items on the product side. Before I balance this reaction, I have 1 silver on the left, 1 nitrate on the left, 1 barium on the left, and 2 chlorines on the left. On the product side, I have 1 silver, I have 2 nitrates, I have 1 barium, and I have 1 chlorine. This reaction is not balanced. In an effort to balance the equation, I'll start by putting a coefficient of 2 in front of silver nitrate on the left. That changes the number of silver and nitrates to 2 each. I have balanced the number of nitrate ions on each side. However, now the number of silver atoms is different. To solve this problem, I'll place a coefficient of 2 in front of silver chloride on the right-hand side. This changes the number of silver atoms on the right to 2, and also changes the number of chlorines on the right-hand side to 2. Now this reaction is balanced as well. At this point, I hope that you are ready to go off and balance some reactions on your own. Good luck.